We try something different today. Uh-huh. We should say which project are you on? Oh yeah. I think Kyle's handling that. You guys might be meeting sometime next week. No, no, like you said I did say anyway. Oh, Data Palooza? Yeah, but like you said that you guys were working on like setting up something in general. Like in terms of getting the initial meetup? In terms of just like actually meeting with like a plan. Yeah, that's what I'm saying. I think Kyle's setting that up. Yeah. For my guy, it's others. It should be in the next another week or 2 weeks. He's out of office this week for some reason. For you guys, I don't know. Should be sometime next week. Did he get your availabilities? Yeah, yeah. All right. Oh, yeah, that should be chilling. Appreciate it. It's from last year. Uh, all right, I'll give it another minute. Hey. No, actually, it makes sense. Oh, fuck. You stay for Tuesday? Tuesday? Is he working on Sunday night? Yeah. I pulled up like yesterday morning. I'm registered to vote here actually, not where I live. So yeah, I had to pull back up here. I didn't feel like changing where I voted, so or I did, I just didn't do it in time. So sorry, give me one more minute. All right, small class today, so yeah, you guys are staying close enough. All right, we're gonna get started. Okay. So today's kind of the first part of a three-part series. Actually, wait, give me one more second. All right, yeah. Today's kind of the first part of like a three-part series on kind of like generative modeling. So today we'll be covering autoencoders. Next week we'll be covering GANs, generative adversarial networks. And then the week after we'll be covering diffusion models. And I think that's kind of the last lecture for this semester. I don't think we'll be doing a lecture for finals, so unless you guys really want one. But yeah, okay. So yeah, so far we've kind of mostly focused on like regression and classification. So neural networks, we kind of know how to like just your base neural network shows us how to do regression or classification on like a list of data, like a 1D list of data. So again, like rows in a spreadsheet, right? CNNs kind of teach us how to expand that idea to multi-dimensional data. So think images, right? Like a grayscale image is 2D. An RGB image, so a colored image is 3D, right? And then RNNs let us, expand this idea to sequential data, right? So think like stock data, right? Words, text, those are all sequential, right? So, kind of in general, what we've kind of been doing under the hood is something called representation learning, right? So again, it goes back to the idea of, if you remember from our CNN lecture, why didn't we just take this 2D piece of data, right? And then just flatten it down to a one piece data, right? And then just chuck that list of pixels into a neural network, right? Why do we bother with all these convolution layers, max pooling? Like, why do we bother with this step in gray or orange, right? So just to review, this is we'll be doing a little bit of a CNN review, but flattening the image just means that we're kind of taking each row of the image, right, and then just rotating it and stacking it row by row, right? So we're not really modifying the pixels. We're just kind of flattening it, right, from a 2D set of pixels to a 1D set of pixels. Does anyone need any more review on flattening or anything like that? Okay. So again, this flattened representation, while we could put it through a neural network, it just contains raw pixels, right? Which is tricky, right? Because the neural network must now learn how to use those raw pixels to make its classifications, right? And images, right? Like if a human kind of looks at this 1D list of pixels, we have no idea that this represents a 5, right? Because we lose all that spatial information, right? When we look at an image, we see how the pixels relate to other pixels, right? So we use in a CNN this convolutional operation, right? And the goal of this convolution is to learn something called a kernel, right? So these are kind of the weights and biases of a CNN. Um, and this captures the spatial information between pixels, right? So just a little bit of review. We take a kernel that's some n by n size. In this case, we have a 3 by 3 kernel. And then we do an element-wise multiplication by an equivalently sized n by n window of the image, right? So here we have a 3 by 3 kernel. We're multiplying it by a 3 by 3 window of um, an image, right? So again, the top left element of the kernel is being multiplied by the top left element of the window, and so on and so forth, right? And then you then sum all those products together, right? So for example, the top left -1 in the kernel is multiplied by the top left 0 of the window. The centermost 8 in the kernel is multiplied by the centermost 238 pixel value in the window, and so on and so forth, right? And then you then sum all these values, right? So you get a 146. Just a little bit of reminder, after you do your convolution, the output that you get, so again, for every convolutional operation, you get a single output. The output is not necessarily a pixel, right? Pixels are from 0 to 256, right? That number could be above 256, it could be negative. Whatever this number is, it's no longer a pixel. Okay. So we take that window, right? We take this convolution operation and we apply it to every single, not every, but we apply it to different windows in our image, right? So in this case, we're sliding that window across our entire image. And each time we get a single convolutional output, right? So we get a single output. Yeah. So we slide across first, and then we then slide down, right? Oops. Okay. Um, so this is just more CNN review. The stride just tells us by how much we slide our window by. A stride of 1, right, on the x-axis just means we had a stride of 1 from before, and that we slid by only one interval, by only one pixel at a time. If you slid by every 2 pixels, that would be a stride of 2, right? So you have a stride in the x-axis and in the y-axis, right? By how much you move down, row-wise. Yeah. So stride is a 2D number. So first element is x, second element is y. And again, we do these convolutions. So each convolution, remember, each convolution uses a single kernel. Each kernel is a different way of inspecting the image. And we learn these kernels, right? So for example, if we're trying to learn how to classify these kind of black and white hand-drawn numbers, we might learn a kernel, right? That learns how to identify like edges, right? We might learn a different kernel that learns to highlight, say, like these kind of gray values on the corner of the image, right? The point is the model has the flexibility of learning a bunch of different kernels to best analyze the image, right? Each layer of our CNN generally has us doing multiple convolutions at the same time, right? So one convolutional layer might have like 3 separate convolutional steps. So that's 3 separate kernels. Again, that's 3 different ways of looking at the image at the same time. Again, just to keep note of, if you do a convolution, you generally kind of shrink the image as you go on. So you can add something called padding to like prevent your image from shrinking too much, right? To prevent you from losing information at the convolutional stage. Yeah. Okay. And so again, right now, the convolutional operation is still a linear operation, right? We're just doing multiplication and additions, right? So to make sure we learn non-linear patterns in our image, we then pass it through an activation function. So it's the same ones we've seen before. In this case, ReLU would work perfectly well, right? So essentially, we're applying ReLU to every single like element, every single cell in our output feature maps. Okay, so back to kind of this idea of representation learning, right? We use these convolutional steps, so convolutions, activations, and then max pooling, right? And then we take that output feature map, and the goal, right? What we hope is that this output feature map, right? Right before we send it to this flatten, right? That's extracted all the relevant spatial features that the model needs to know. And now we flatten this, right? Since that feature map is just an encoding of important information, when we flatten it, we don't lose anything important, right? So that's a little bit of a jump in logic you'll have to make a little bit, right? Again, pixels lose meaning when you just kind of unravel them, right? An individual pixel on the screen makes no sense unless you see the pixels around it, right? The goal with these convolutional layers is we can learn this non-interpretable multi-dimensional matrix, right? Such that when we do flatten it, right, the neural network can operate it and it's condensed, summarize all that spatial information into this 1D list. Does that make sense? And again, we don't really, if we look at this, if we look at what we have after the flat, we won't understand it whatsoever. But the hope is that the model, like it's easier for the neural network to process it because it retains spatial information. So another term for this kind of this output at the flattened step after a the CNN's block is called a representation, right? Because we want to we learn how to represent an image into this 1D vector, right? As opposed to just squishing the pixel and just feeding that raw vector into the neural network. Okay, and so you can kind of like rethink your convolutional steps as learning a representation that we could then easily feed into a neural network. So this block is just making, the neural network's life a lot easier. We're learning a useful representation. So we can kind of separate this, right, our neural network into two blocks then, right? The first block, we can think of it as an encoder that takes our image and encodes it into this representation that a neural network can then use. And then we can think of our neural network as a separate block that takes representations as input and then does some classification task, right? But we could then kind of generalize this idea into, okay, so we have an encoder that learns to like represent the original input, right? I then have this other block that could do whatever we want with that original representation, right? So traditionally in the task of like image generation, we have something called a decoder that learns how to use a input representation and modify it and generate a new image, right? So this is what an autoencoder is, right? So the autoencoder has two blocks, the encoder and the decoder. And the encoder's job is to use whatever mechanism to learn a useful representation. So we call this representation a latent representation. You might hear me use the term latent vector. I'll be using those two interchangeably, right? And then it has a separate decoder block that learns how to use a latent representation to generate whatever kind of output we want. So in this case, we have a blurry input, right? And the decoder's job is to generate, given a representation, generate the unblurred version of that input. Okay. So again, this is kind of the architecture of a autoencoder, kind of back to like the simple 1D neural network structure, right? It's really not that different from what we've seen before in this case. Again, we're not working with images right now. This is very simple autoencoder. Um, this encoder block, again, it takes a flat vector as input. It's just a simple neural network, what we've seen before, right? Input layer, hidden layer, output layer, but this time the dimensions of the output layer, like the sizes of it, dictates the size of our latent representation, right? And what we want is for our latent representation to be smaller than our original input. So in this case, our input's like what? 1/5. Our latent representation is now 1/3, right? So why do we want to do that, right? Why can't it just be the same size? Well, again, the whole point of the latent representation is to learn a better way, a better representation of the input, right? So you can assume, like, for example, in an input, right? If our goal is just to, like, if you think back to a CNN, classify cat or dog, right? We don't need all that information in the background of the image, right? We just need the core features of a cat and the core features of a dog, right? So you can assume like the job of the encoder is to summarize and like break down an image. The problem is if we allow the latent representation to be the same size as the input, well, our encoder just might learn to not modify the input, put all of the work on the decoder, if that makes sense, right? So we run the risk of learning the identity function, right? As in just the neural network learns to never change the input image and just forces the decoder to like do most of the heavy lifting. Okay, so the decoder takes as input the latent representation, and then as output whatever output we want, right? So we don't really see an autoencoder used in this kind of 1D example very much. Um, you might see to maybe like transform or modify like rows of a spreadsheet. But again, generally the output size of the decoder is the same as the input size of the encoder, right? So it kind of has this symmetric look to it. Okay. So a very common type of autoencoder is the deblurring autoencoder, right? So again, given a blurry image, unblur it. So again, we don't want to just flatten an image and then chuck it through our encoder, right? We want to, can we use kind of the ideas of a CNN to make this process easier? But before I get into that, um, our job actually in this case, like normally when we're working with images, it's really annoying, right? Because we need someone to like hand annotate, is this a cat image? Is this a dog image, right? You can imagine for image transformation tasks, this is even harder, right? Um, but a lot of autoencoder tasks are what we call self-supervised, right? Remember, we have supervised, unsupervised learning. Self-supervised learning is just a subset of supervised learning. The difference is we can derive our labels, like our ground truths, super easily from our input without really like, we can basically automate it. So for example, if you want to train a deblurring model, right? We can just take an arbitrary set of images that we want to deblur, and then just deblur them ourselves, right? We don't need a human to like manually deblur it somehow. We can just write a program to just like pixelate stuff, right? Which I have here, right? So in self-supervised learning, again, it's still supervised, right? We still are uh, our inputs still require having output labels. It's just trivial to derive those labels. Does that make sense? So you see a lot of self-supervision in like your language models, your NLP, but we'll get into more of that like I think next semester. Okay. So anyways, back to like trying to make this deep learning autoencoder. Um, so in this case, we'll kind of follow the structure of a CNN. So our encoder is actually just pretty much a CNN, right? Minus the dense layer, right? So we have our convolutional blocks, and also like a max pooling block if we want, right? Now, what's more interesting is our decoder block, right? So we still have our ReLUs interspace between what we call transposed convolutions, right? Um, yeah. And so again, just a little bit more on our decoder. Remember, sorry, encoder. Our latent representation could be whatever shape we want, as long as it's like roughly smaller than our input. So it could be, we could have as many, in this case, feature maps as we want, right? So it could be some, if our original input is like 20 by 28, our latent representation could be like 3 by 2 by 10 or 3 by 2 by 5, whatever. We can have as many 3 by 2s as we want. Um, yeah. Okay, so again, the encoder's job is to use convolutions and possibly max pooling layers to shrink the information. Again, we don't really need to flatten in this case. The whole reason why we flatten is to feed into a neural network, which we're not really doing right now. We could stick a neural network here if we want, but in this case, it's a pretty simple problem. We don't need to. Okay, so the decoder's job, taking latent representation, learn to upscale it, right? So again, we want to kind of do the reverse set of operations in a sense and expand this latent representation back to the original size of the input, but this time we've modified that input. So our upscaling operation is called a transposed convolution, right? So we're still using a kernel, which is learned, right? So these values in the kernel, think of them as weights and biases. And we're still multiplying them by a equivalently sized window in our image. The difference, though, is our output is larger than both the input and the both the window and the kernel, right? So again, we still have stride and kernel, and I'll get more into the sizing a little bit later. But essentially, unlike a CNN, a convolution, where the stride, increasing the stride decreases the output size. In this case, increasing the stride increases the output size, right? So for example, let's say we have a stride of 1 and we have a 2x2 image, right? So it's this example, right? What a transpose convolution does is we have a 3x3 output and we multiply this entire kernel by the top left elements in our window, right? So this 2x2 kernel is multiplied by 3, and that's how we get this top left 2x2 thing in our output. Again, we repeat the same process for every single cell in our window, right? So again, 2102 multiplied by 1, right? And that 2x2 output is now the top right of our output, right? So you can kind of see, again, we multiply by the bottom left element in our window and then our bottom right element in our window. And so we now have these four 3x3 matrices, right? And so kind of these L shapes are all zeroed out, right? So the idea is we just add all of these up. We add these four 3x3 matrices up, and that becomes our final output, right? And again, if we want a larger than a 3x3 output, right, we can just increase our stride, right? So in this case, in our stride of 1 example, right, you can see that these like the output of the top left pixel and the output of the top right pixel, they kind of overlap in the central column, right? If we increase the stride, we no longer have that overlap, right? So again, this top left pixel, its outputs kind of dictates this 2x2 region, which does not overlap with any other 2x2 region on the screen. So again, just to recap, increasing the stride increases the output size. And then in this case, padding actually decreases how big our output image is. So we actually don't see too much, we don't see too much padding in transpose convolutions traditionally. Okay. And again, the whole point of a transpose convolution is to learn how to upscale our image. We're not just like doing this at random, right? And again, I've been saying that it's the inverse of the encoder, but that's really structurally, right? It's structurally the inverse, right? So again, this convolutional layer, for example, is the same size as this transposed convolutional layer, right? But the kernels are completely different for both. Does that make sense? Okay. Does anyone have any questions about the structure of this? Oh.
So, suppose
Mhm.
this to look like a convolution or
It's not intuitively, it's kind of reversed in that a convolution without padding decreases the image size, and a transposed convolution increases the output size, right? Aside from that, it's not exactly the inverse. Like mathematically, they're not inverse operations. Yeah. Yeah. So what are some other use cases of autoencoders, right? Generally, you'd use this kind of autoencoder for an image-to-image task, right? So given an image, make some change to that image, like add stuff, remove stuff, and then get your output image, right? So for example, a very kind of toy example of this is like filters, right? So take an image of the summertime, right? And then transform it into the equivalent image, but in the wintertime, right? Like, I don't know, like early Snapchat filters could have possibly used autoencoders, right? Because they're taking your original image and then overlaying stuff on it, right? Keep in mind though, this kind of image to image task is really hard because it's not self-supervised, right? Yeah. Like how would you'd actually need to photograph the same landscape in your training data during the summer and during the winter, right? So this kind of image to image task is usually pretty tricky, just because there isn't too much data for it. Okay. Another very common use case is called image segmentation, right? So the idea is that you have your input, right? Let's say like an MRI scan, right? And your output is again the same MRI scan, but this time it highlights different regions of the output or of the input image. So for example, like if you want to highlight like tumors or different types of diseases in your MRI scan, right? Once again, this is not self-supervised. But especially in the case of medicine, there's a ton of training done out there, especially with MRIs, with bones, with injuries, things like that. Um, Kind of the most common type of autoencoder that you'll see for this image segmentation task is the unit autoencoder. And again, what defines a segmentation task is that you're creating masks or outlines of specific outputs, right? So you might have heard of object detection. That's an easier version of segmentation. For object detection, you just be drawing boxes, like literally a rectangle around these rough regions, right? So like this green spot, for example, we just have a box around it. We wouldn't have this level of precision. Segmentation gets the exact outline of what we want. But yeah, okay. Another common task is super resolution. So it's very similar to deblurring, except that you just take a pixelated image and then just increase the scale of it. This is a very common task, actually. It's also self-supervised, so it's very easy to train. Autoencoders are actually not the leader in this field, I think. I think it's GANs or like diffusion models. But early super resolution tasks were kind of done by autoencoders. Okay, so another really useful use case for autoencoders is something called feature extraction, right? So the whole idea is given we want to take a large input and then we want to condense it. So actually the goal of feature extraction is this latent representation, right? Normally we should use the latent representation as a feeder to the decoder. In feature extraction, oftentimes what we see is that we might have an input that's really long, right? So think of a spreadsheet that's like hundreds or like thousands of columns long, right? So what happens if we try to put that, hundreds of thousands input sequence into a neural network? The neural network gets really big, right? And why do we not want like a really big neural network? An arbitrarily big neural network. No, sorry, I think you were saying. All right, let me help you a little bit. What happens if we have a really big neural network where all the input features might not be relevant? Overfitting, right? So there's something called the cursive dimensionality, and that the bigger the neural network gets, so you can almost think this is not the exact relationship, but as you linearly expand the number of neurons, right, you roughly need to exponentially have that much more data, right? Um, it's not that exact relationship, but you can intuitively think it like that, right? So if your input sequence is really long and you're forced to have, a massive neural network, right? You're gonna be affected by cursive dimensionality. You're gonna need a lot of data. You won't have that much data, and you'll end up overfitting, right? So the whole point of this is that if we could yeah, kind of just explain that. Yeah. So the goal is to condense this really long representation, or sorry, really long input. And then if our latent representation, well, summarizes the relevant bits of our input is just smaller, why don't we just feed that latent representation into a smaller neural network and avoid the overfitting problem, right? Assuming that the latent representation describes the input really well. Shoots.
The entire point, like the downstream task of the whole latent representation thing is like do something with that neural network, right? They're feeding it with.
Yeah.
So does like the encoder decoder block actually work better than like your standard just regular encoder?
What do
Like
you?
you have like a CNN is gonna do the same thing as your encoder decoder block.
So whoa. So like,
But like in the sense that it's making a latent representation. Like CNN makes a latent representation that it flattens and feeds into the neural
yeah,
network. This is doing the same thing. Like, is this better at it basically?
not exactly. So, your encoder is these convolutional blocks.
Yeah.
So like in a CNN and in autoencoder, like the CNN portion and the encoder portion would be identical. So it's not necessarily better.
Well, but I mean, this is trying to do the same thing.
Oh, I see. So are you saying the latent representations of an autoencoder better than that of a CNN?
Yeah.
So not necessarily. Yeah, that's a good question. So for a CNN, you're traditionally doing classification, right? So your latent representation, like it only captures the stuff relevant for classification, right? Um, Whereas to like, in the for an image to image task where you're generating new data, you'll probably have to capture more information about the image, preserve more data, right? So a CNN block, right? You probably would have a smaller, more condensed latent representation that's more efficient. Whereas in an autoencoder, your latent representation is probably going to have to be bigger, but it captures more information. So better in different ways. Good question, though. Yeah, so back to feature extraction, right? Again, we want a really good latent representation that learns to summarize our input, right? So again, if our goal is just a latent representation, well, we could just have our output, like our label, be the exact inputs, right? So we just train the autoencoder to just crunch down the image to a latent representation and then reconstruct the original inputs. And then once we've done that, right? By the way, so the way we would train this is the loss function would just be the reconstruction loss. That's literally just calculating the mean squared error between the outputs and the original image for every single like pixel, right? Uh, so yeah. Any question about reconstruction loss? It's just mean squared error on every cell of the image. It's just reconstruction because, well, you're reconstructing the image. Okay. Just when you see this terminology in papers or in later lectures, just assume it's mean squared error on the pixel level, and then you just sum them and then take the averages across all pixels. Okay. So again, train an autoencoder, where the encoder learns the latent representation, decoder learns to reconstruct the input. And then, right, once we deploy this model, right, we just chop off the decoder, right? We chop off the decoder, we feed the input into the encoder, and then train a neural network to do whatever task we want the original neural network to do. Does that make sense? So for our original neural network, let's say we're doing stock price stuff, right? Our original spreadsheet has hundreds of thousands of lines, right? We would still have that stock predictor neural network at the end. It's just it takes the input of the encoder instead of operating on the spreadsheet directly. Um, Honestly, in the modern day, I would say that when you see an autoencoder, you would see it used in this kind of feature extraction case the most, at least in my experience. Um, yeah. So again, you can get away with having a small neural network, right? And so when you're training the small neural network, you just wouldn't train the encoder. You just treat it as a normal function, freezes, weights, and biases, kind of like that. Okay. So yeah. So again, we use this encoder decoder for either feature extraction or for taking input and transforming it, maintaining its size, right? But what happens if you want to generate like a completely new image? Right? Like a lot of you, when you think of image generation, you think of like Sora, right? Or like VO3, right? In that case, you just put like a text prompt, usually a pretty bad text prompt, right? Like one sentence long, and you get this like beautiful, huge image, right? You're essentially generating something from like almost nothing. In theory, you could just like give VO3 nothing and then have it generate something spontaneous, right? How do we kind of do this more spontaneous generation? Well, we'll get to that later. For now, okay, I'm gonna run a Kahoot. Should be no more than 5 minutes. Um, I'm gonna see like we only have 3 more lectures this semester, including this one. So I might keep track of winners and give someone a free t-shirt based off like
Free t-shirt.
who does the best across all the
We
quizzes.
get the t-shirts first.
Yeah. When do we get our t-shirts at some point? There will be t-shirts. Inshallah, one day. All right, hop on the Kahoot. We'll see who's paying attention. All right, Shoobs, hop
I
on,
wasn't
bro.
paying attention. I'm not hopping on.
Hop on, Shoobs. Hop on, Shoobs.
My ego.
Use an alias, bro. Use an alias.
There's like 5 people.
No, yeah, people using their government names, Loki. Yeah, okay. See, like, if you copy someone's name, though, they won't know it's you.
There'll just be 2 Shazaves.
Ah.
Ooh, how many
All right, hop on, Shoobs. Hop on, Shoobs.
You want me to?
Yes. All right. And I'm doing 10 seconds per question, by the way. I like to keep this shit quick. Oh. All right, Shoobs. If you don't win this, you're not getting a promotion.
Oh, damn. Wait, I don't know autoencoders. Read my DMT homework.
Oh, where's the music? Yay, everyone got that right. That wasn't too hard. All right. Okay, okay. Okay, Ox. Fast with it. All right. You're right. Yeah, so this is a little bit of a tricky one, right? So when you think of grayscale data, you might think that like grayscale data is still 2D, it's still multidimensional. Neural networks can only accept a 1D input. Yeah, I'm proud someone fell for that. I had to think of how to make this a little bit harder. All right, all right, all right. Ox still in the lead. Yeah, these are like easy questions. I put all the hard ones for the second section. This is my one free image, by the way. They didn't let me have section. No, it's just the second half of the. Oh, okay, okay. Let me see. Classifies the image, learns to reconstruct the input, drains random noise. Yeah, so the decoder does the reconstruction part, right? Encoder learns to extract key features, learns the latent representation. Decoder does the reconstruction. All right, London's popping off. Okay. Oh, what the fuck?
What?
All right, that's my bad. What the fuck? All right, that's on me. Correct answer was fuck. No one got that. Good, right? Yeah, I think that was just a misinput on my part. What the fuck? I'm gonna have to fix that for next year. All right, no damage done. Uh,
What is that saying? Okay, that's a bad. What is it?
all right, the latent vector should be oh fuck. Should be at least as large as the input, so we can learn more complex math.
These purple hot We're
50.
impeaching you.
50-50, bro. 50-50. All right. Yeah. So it should be at least as large. So like we don't, it should be at least smaller than the input, really smaller than the input. Yeah. Yeah. That little block on the top was a little bit unfortunate. I don't know what that was. Hey, shoot. Hey, you profited from that.
I'm
Alright.
still impeaching you.
What kind of learning is used when the target output is generated from the input itself? It's like deep learning. What kind of task is deep learning? Deep learning, not deep learning. Yeah, everything got self-supervised. All right, nice, nice, nice. All right, shoots. All right, let's just what's the purpose of this thing? Wait, what the fuck? All right,
Two randomly.
all right, that's my bad. All right, no one chose it. Good. That's my bad.
You gotta be kidding.
Fuck. All right, all right. That's my bad. I had more errors than I thought it did.
Gee, when you make this, look at that.
Maybe last week. Yeah, okay. So it doesn't do object classification, right? So again, image segmentation is what it does. Object detection is not really an autoencoder task. Yeah, all right, all right.
Yeah, assign
All right.
officer take a food duty.
Right. All right. So the second half, all right, shit, I might actually have to low-key like read the answers for the next section. All right. So there is a second half to this lecture. So we left off on the question of, okay, so autoencoders, right? We go from one image and transform it somehow to another image, right? What happens if we want a more spontaneous form of image generation, right? Okay. So again, the goal in this case of like data generation in general, right? We kind of want a new set of images that kind of look like our input data sets, but aren't copies of it, right? So, okay, kind of a naive way of going about this is we take an autoencoder, right, that reconstructs its input, right, kind of the feature extraction autoencoder, right? And then, okay, the question is, can we then train this autoencoder reconstruction task, chop off the encoder bit, and then tweak the latent representation to then get a new spontaneous output that maybe looks like this original input, right? So again, if we want a new generation of a 5, right? Could we just take a known 5 latent representation, like save these at the end of training, right? And just tweak it a little bit and get a new image of a 5, right? So again, this is just a visual representation of doing that, right? So again, if our input representation is 67.27, and we know at the end of training, this maps, we stop training our decoder, right? If we input this latent representation, we'll always get this exact image of a 5, right? Could we tweak it a little bit? So 6.4, 6.8, 6.8, and then get a new number 5 image, right? So this would be pretty nice, right? Because if we still want to generate images of a specific class, we could just pick linear representations from that class, tweak them a little bit, and get images from that class, right? Um, okay. The problem with this, right, is that there's no guarantee similar latent representations have similar outputs, right? So for example, let's say from training, right? We know that these are two known examples, two latent representations, that if we feed them to the decoder, we'll get these outputs, right? And we know this from training, right? Some input training data, like, sorry, but this arrow is more so like representing the encoder, right? So from the encoder, right? If we input this number 5, right? Again, we're doing reconstruction, right? So we input this number 5, the encoder will then give us 67.27, and the decoder will spit us back out the same image, right? Both of these image, they're known, right? So, let's say we sample some vector that's in the midpoint between these two known working vectors. Well, we have no guarantee, right, that this similar latent representation, this red one, right, will also generate a 5, right? So again, we can kind of this kind of falls on this idea of a theoretical latent space, right? So this latent space is the size, so it has a number of dimensions equivalent to the dimensions of our latent representations, right? And you could think that all possible latent representations, we could just map them into latent space. So for example, if our latent representations, so in this case, they're 3D, right? 1 by 3, but let's say our latent representations were 2D, right? Well, we could just graph them on this 2D Cartesian plane, right? Again, when you make these autoencoders in practice, there is massive multi-dimensional space impossible to graph, but you could plot all of your vectors on this latent space, right? So again, what we would find after this autoencoder training, that again, similar latent representations do kind of cluster together. They are nearby each other in this latent space, but there's no guarantee that this white space, an arbitrary vector in this white space, also points to something that makes sense. Like we can only have guarantees from the data samples from training, right? We never really made sure that white space mapped to anything, that empty space had any like semantic value, right? So what we really want is our latent space looking something like this, right? Where we kind of have these blobs, these areas that all kind of map to something, right? So of course we can't fill this massive 2D space. We can't plot, it's continuous, right? We can't plot every single possible value and map it to an image. Instead, the hope is if we just plot a couple, right? A couple points or a couple latent representations, we can kind of fill in the gaps, right? So we want to have a latent space that looks like this, right? And kind of enforce this condition of filling in white space or empty space to actually map to something meaningful, right? And that way we could now we can, if we kind of have a latent space looking like this, we can then sample a latent representation, let's say in this blue region, and guaranteed get a 5. It might not be a nice looking 5, but it will be a 5. It will be an image, and it won't be some like white noise garbled mess, right? Okay, so how do we kind of enforce this condition of learning a nice, continuous, well-represented latent space? Well, if we kind of go back to our number line representation, we want then like for every single dimension, the 6, the 7.27, so our three-dimensional vector, right? We want for any given latent vector, we want everything within a certain range to map to an actual image, right? So in this case, right, we can map all numbers around the 6, let's say 5.5 to 6.5, right? And we can map all numbers in that range, or sorry, all layer representations kind of sampled in this space to the same input image, right? Yeah. Does that kind of make sense what we can kind of do here? So we'll take latent representations, right, that are within some range of a known latent representation from our input and map them all to like the same image or different images in training. Does that make sense? Okay. Yeah, okay. So before we do that, so kind of the how we'll do that relates a lot to like probability. So just a quick review of prob and like little bit of stats, I guess. So a normal distribution, right? So it's a type of probability distribution in which the x-axis is really any variable, and the y-axis represents the probability of that x-axis value being sampled, right? So for example, you can see that for this normal distribution, the probability of picking a 2 from our data has the highest probability, right? That's what that y-axis represents. So for example, let's say we have a distribution representing the number of eyes on like the UVA campus, right? So you would expect that the average number of eyes a person has is 2, right? So you would see that you have a spike, right, on the number of 2. You have the highest probability of if you pick someone in our UVA campus, they'll have 2 eyes, right? Yeah. The probability of someone having, so again, like if we pick the number of people, or sorry, count the probability of the number of people that have 1 to 3 eyes, right? To calculate that range, that probability range, we can just calculate the area under this curve, right? So in this case, calculating the area under curve, that's just calculating an integral, right? It's just pretty easy. And we do that with any range on our normal distribution. Okay. In this case, calculating the number of eyes between people, sorry, the number of people who have 1 to 3 eyes, that's roughly 68% chance that we will sample someone with that range of eyes. Whereas 3 to 5 eyes, it's very, very rare. A 16% chance in this weird distribution. Reality is probably like 0.01%, but we have a very wonky normal distribution. So again, intervals closer to the center naturally have higher probabilities, right? Um, okay. So again, to characterize this normal distribution, we can actually describe any normal distribution with just 2 numbers, the mean and the standard deviation. So the mean is just the average value of our distribution of our data set, and that's where the peak is located, right? So again, that makes sense, right? Like if we look at our number of eyes, right, and we say that the average number of eyes is like 2.1, 2.2, right? Well, 2.1, 2.2, that's the most likely value to be sampled. So that's where the center of our normal distribution will be located. The standard deviation represents how spread out the values are, right? So again, a standard deviation of 1 has a little bit more of a narrow shape, right? There are, way less people with 6 eyes compared to like 2 eyes, right? Whereas a standard deviation of 2 has a more spread out probability, right? So you can imagine, if our distribution counts the number of eyes, we have a super narrow standard deviation because like people tend to have 2 eyes or like 1. No one really has 3 eyes, right? The standard deviation is probably like 0.001 or something. Yeah. So again, we could describe any normal distribution just by the mean where the distribution is centered and the standard deviation describing how wide the normal distribution is. Okay. And again, like every normal distribution, right, that has a given mean standard deviation will always look like that. There's no variance, right? Does that make sense? Right? You could characterize any normal distribution just by their mean standard deviation. Okay. So back to kind of this idea of autoencoders, right? So given an input, right, a standard autoencoder will generate a latent representation, right? In this case, we have a 1D latent representation, but the point is, like we're outputting individual numbers, right? Like each value in our vector is just a scalar. If we wanted to kind of expand this to like learn a range of numbers, so again, transform this into what we call a variational autoencoder. Instead of a 1 by 3 output, our model would learn a 2 by 3 output, right? So for every dimension, we would learn a latent distribution instead, right? So for every dimension, we output the mean and the standard deviation, right? And so the idea is that we map that normal distribution to the inputs as opposed to mapping a single vector to the input, right? So by mapping a normal distribution to your input, you values or like you can assign chunks of your latent space, like let's say regions in your latent space, to a single value to an output, as opposed to a single dot as a single point in your latent space to an output, right? Yeah. So again, if in an autoencoder we had a 1 by 3, latent representation, and a variational autoencoder, which is what we've kind of been building up to now, would have a 2x3 latent representation. One dimension being mean, the other dimension being standard deviation. Okay, and again, we'd have a separate normal distribution for every dimension of a latent vector. Okay, so let me kind of, so yeah, so this is kind of the visual you should have in your head, right? So numbers are really hard to see, but originally we had, this 5 mapped to a 6, 5, a 6, a 7.2, and 7, right? What we're essentially doing is taking like this interval around the 6, right? And mapping this, right, to this input of a 5, right? So now we can capture spots of our latent space, regions. The reason why we want a probability, right, is that areas in our latent space that are closer to what the original latent vector would have been are more strongly mapped to this number 5, whereas the farther we get away from this number 6, the less those values map to the original input. Okay. Yeah. So how do we actually kind of enforce this idea of mapping a region to an input, right? Like how do we actually make sure our model learns to use means and standard deviations instead of just an arbitrary set of two values, right? So what we do is that instead of directly feeding these two numbers into an autoencoder, right? What we do instead is randomly sample, right? We randomly sample a vector from this latent distribution and feed that number into an output, right? So for example, for every distribution in our 2x3, in our 1x3 distribution, right? We sample a different number, right? So that way we can sample a bunch of different points. Yeah, we can sample a bunch of different points in this distribution and they all map to the same output, right? Does that kind of make sense? Right. So, what are the mean and standard deviation kind of mean in this case, right? Um, so again, the mean is the true, you can think of it as like the true latent representation of the input. Like if we were just using an autoencoder, right? What would the latent representation of this number of this image look like, right? That's where the mean is, right? The standard deviation is how far away from that true latent representation can we get and still have it look like the original input, right? So for a large standard deviation, right, we can go like uh yeah. So for a large standard deviation, like we can go really far away from the 6, 7.2, and 7 and still have it look like a 5. Whereas for a small standard deviation, um, you know, we would have to stick very close to the light representation. Yeah. I think I swapped the graphics between these two slides. Yeah. Okay. Sorry about that. Okay. So before, if you kind of remember the visual I had like clearly like separated out masks. In reality, what our latent space now looks like, kind of these like Gaussian, like kind of like these gradients, right? Again, like the closer you get to like specific to actual known latent representations, um, the more like it maps to like a 5. The farther you veer away from like those inputs and training data, the less they map to a 5, but they still map roughly to a 5, right? So what does that kind of mean? But yeah, so by the way, like if you could just by eyeballing this, for example, right? You can see that this distribution probably has a very small learned standard deviation, right? Whereas this distribution, right, like you can go very far away from these green dots and still have that sampled vector look something like a 7. Okay. So what's actually kind of interesting is like you might see regions of overlap, right? So okay, it's kind of hard to see on the screen, but the green distribution and the blue one are overlapping, right? So in theory, if you pick a vector that's in between the space, you might get something that's like the combination of both. So this weird 5-7 looking thing. And yeah, so again, if we want to generate new images of 7s, we just sample something in the 7 distribution space. Yeah. Yeah. Does that kind of make sense? It's just kind of a summary slide.
So our mean and our standard deviation across them all are like parameters. And like during backprop, we're backpropping through and like fixing our mean or standard deviation.
Sort
See
of.
how similar it is to the
Yeah.
output.
So the mean standard deviation are more so intermediary outputs. The encoder learns how to produce those.
But
Oh, I see what you're saying. Um, I see what you're saying. So generally, you could have a separate parameter, like a fixed parameter, like a hyperparameter that chooses how much of a standard deviation you want, that scales your standard deviation or mean. Yeah, like you wouldn't really have a hyperparameter that moves around your mean, but you could have one for your standard deviation. Does that make
oh
sense?
yeah, you wouldn't have one that moves around, but you would have because like each of the features have like a different standard, like each dimension in your latent
Exactly.
has a different standard deviation.
Exactly.
So that like through training, I would imagine you're like changing that over time. Like you have to
Exactly.
learn what that standard deviation is.
Yeah. You learn whatever standard deviations works best, right? Um, yeah, there are hyperparameters to like force you to have a bigger standard deviation. So you're not all your latent vectors aren't too close together. Yeah, some an analog of that. Actually, not really. Actually, yeah, I guess that kind of would be temperature. Generally, actually, you want a smaller standard deviation just because like it's a lot easier for the model to learn to map latent representations in a similar space. Um, because like again, we're working with a very, very large multi-dimensional space. Right now, I've just been talking about like 1 by 3, 2 by 3. In reality, we have a ton of dimensions here, right? Like 5D, 10D, whatever, right? So if we have a really big standard deviation, it becomes really hard to sample vectors, right? Um, but yeah, good question. Okay, so the loss for training a VAE, so it's still a reconstruction loss, right? Because again, we're still mapping inputs. Yeah, like we're still learning to reconstruct stuff, right? It's just that we're um instead of learning to assign a single lane representation to its original input, we're assigning like a group of lane representations to the same input, right? So we're still doing reconstruction, right? But we also have this other term called the KL divergence, which we covered in class today, Shubes. Yeah. So again, reconstruction loss, same thing, mean squared error, right, on the pixel level. So KL divergence is the Kullback-Leibler term. Um, so essentially what it's measuring is given two distributions, right? How similar are they, right? And the B is a hyperparameter, usually between 0 and 1. That just tells us, how important that second KL divergence term is, right? So a little bit more on the KL divergence term, right? The higher the KL divergence is, the less alike, the more those two distributions diverge, right? So you can imagine that these two distributions, they look very different. So we'd have a high KL divergence term. Whereas these two, right, they look almost identical to each other. We'd have a very low divergence term, right? This is a wrong form. This is the discrete KL divergence term. Um, Actually, well, in practice, we use a discrete one more actually. We'll kind of break this down more in a future lecture. We actually don't have too much time for that. But for now, just think of it as a single scalar term that given a distribution, two distributions, compares how similar they are. Higher, not very similar. Lower, very similar. Again, divergence, that's kind of what divergence means. Okay, so that's what KL divergence is. There's one more thing, right? Before we kind of round out this lecture, right? How do you do gradient descent when you pick a random value, right? Because again, when we're kind of doing our decoder part, right, of a variational autoencoder, right? We randomly sample a vector from the lane distribution. So for example, if our lane distribution is one dimension, right? We randomly sample a number, right? And then feed that into the decoder. How do you do backprop on a random value? Well, you can't, right? That randomly sampling something is not continuous, right? It's definitely not differentiable, right? So we're kind of stuck. What do we do? So you see this a lot in more probabilistic models that use distributions. It's called the reparameterization trick. So essentially, instead of directly sampling a value and chucking that into the input, or sorry, into the decoder, we instead sample a value from the standard normal distribution. So the standard normal distribution is a special type of normal distribution that's centered at 0, with a mean of 0 and standard deviation of 1, right? And so a little bit some stuff from stats. We can go from any standard normal distribution. So again, mean 0, standard deviation 1, to any normal distribution, right? By multiplying some sample value by the standard deviation and adding the mean, right? So again, if we have, like, for example, let's say we have a a normal distribution with a mean of 6, standard deviation of 1, right? Well, we could just add any sampled value from our standard normal, add 6 to it, and it's effectively this distribution, right? So that way, right, now we can take the derivative of this term, right, with respect to the mean and standard deviation, right? Because now this epsilon, the sampled value from our standard normal, that just becomes a constant that like goes away in differentiation, right? Or sorry, that's differentiable. So again, the mean standard deviation, right? We would like these are intermediary values that are outputs through our neural network. So we'd want to backprop on these at some point, right? So they're part of our bigger channel. What's the derivative of the mean? With respect to x, that's just 1. What's the derivative of the standard deviation? Well, that's just e, right? So now differentiation works once again. Again, functionally sampling something directly from our original distribution and doing this reparameterization trick, like they're the same thing. Like we're sampling the equivalent values, just reformulating, like sampling from the normal distribution, multiplying the mean, or sorry, multiplying the standard deviation and adding the mean back. That just makes this process, this sampling operation, differentiable and continuous. Make sense? All right. So review, variational autoencoders. Unlike a traditional autoencoder that learns to map an input to a single latent representation, a single vector, we're learning to map an input to a latent distribution, right? So we're learning a bunch of probability distributions across every single dimension. A decoder, the decoder part though, I want to emphasize is the exact same between variational autoencoders and autoencoders, right? We're still taking a single layer representation and then expanding it back up to the same output, right? It's just the encoder and some intermediary steps before we get to the decoder that changes. Yeah, and so if we want to do image generation, right, with a variational autoencoder, traditionally what the workflow is that we do a reconstruction task, right? Again, via fives, we learn how to generate back those original fives. And then when we want to do the image generation, right? Think of it as your inference step. We just chop off the encoder, take the known latent distribution of an image we want to be similar to, and then just sample something from that latent distribution, and we're good, right? Okay, that's it. We'll do the rest of the Kahoot now if you guys want to stick around. But yeah, if you guys gotta go though, now would be a good time, but let's round out the rest of the Kahoot. So yeah. All right, are you three staying? All right. All right, I'm gonna start it then. You guys ready? Oh shit.
Thanks, Joffrey.
See you, London. Actually, man, did you reset your score? All right, y'all ready? All right, I made these ones a little bit harder.
Uh-oh.
Where's the sound? Where's the music? Yeah, you guys got that all right. Okay. Yeah, everyone got that one.
I haven't done a Kahoot in so long.
Dude, in high school, like Coast with you didn't do any at TJ.
Not really.
Dude.
What class did you have Kahoots?
I don't remember. I remembered. I think I did them in my like humanities classes.
I didn't get them.
All right. I think I'm gonna put Kahoots in all my lectures now. What do you guys think?
I like it, but then you have to like make the content short. People people can only stay for like an hour.
That's fair. I mean, the Kahoots, them all right, Shoops, appreciate it. The Kahoots themselves though, they're like 10 seconds each. So it's like
And then you gotta explain your questions. You have to back that up.
just get them all right. You guys get them all right. I don't have to explain. No, that's a good point. Um, yeah, you guys got it right. See, I don't have to explain shit. You guys are on top of this. All right, it's an or, by the way, not an and. I have an autoencoder, by the way, not a variational auto. I know got that wrong. Okay, maybe these aren't. Maybe these aren't.
You said it wrong. It's true. It's true, but you said false is right.
Oh fuck. Oh shit. That's my bad. Ah. All right, this is good. Oh shit, no one, everyone got the same answers. All right, this one's supposed to be the hard section. Double points, yeah.
Wait, how is it? How is it not? Kale divergence. Oh, what does mean?
Wait, no, I think it's
Oh, I guess that's true.
Wait,
Reconstruction versus regularization. I saw kale divergence and I tunneled on it.
no. It's supposed to be blue.
Well, reconstruction versus regularization could be right because the point of the
Yeah, it's not really regularization though. Or what? Actually,
kind of is right because it's like
oh wait, it
how-
kind of is,
how
yeah, because it
normal
looks
is your-
normal. Yeah.
oh, is your- This is lovely. Yeah.
Yeah, this is a bad question. I should mark both of them right. Yeah, because it is kind of regularization. It is regularization actually. Actually, green is more right.
Yeah.
Because yeah, it's not really mean SCD coupling because this is a nonsense term.
Yeah, like it doesn't make any sense.
Yeah. Oh yeah, wait, no, it is green. It is green. I forgot.
It was great, yeah.
Yeah, made these last week. Shit, I had ChatGPT come up with the wrong answers and fucking fooled me, bro. I was
That's
like,
a good wrong answer though.
that's a good wrong answer, yeah. That's on me though for not explaining this part a little bit more. Yeah, the KL divergence is meant to make it's meant to make your distributions more normal looking, right? So we're doing the divergence between like a normal distribution and the output for each.
If you didn't
thing.
have a kale divergence, it would just be a spike. Like there would be no standard deviation. Right?
Exactly. Yeah. If you didn't have the KL divergence term, we have no guarantee that we're learning normal distributions. We just have like, yeah, we just have like two basically random numbers.
Well, I mean, you would want it. You want the mean
Actually-
would probably be right. The mean would be close to the value. 'cause
It-
you're predicting
We
the
have
reconstruction.
no guarantee that we learn a mean and standard deviation. Like we're just learning an additional two dimensions.
But I mean, like if you think about a normal autoencoder, right?
Mm-hmm.
The mean, like if you isn't the mean just like the normal autoencoder?
Yeah. But the thing is like without the KL divergence term, right? How does that not just become a like just adding an extra dimension to your latent representation?
It literally it is.
Yeah, so we're just adding a separate like it's no different from a normal latent representation. Like
Oh yeah.
there's no idea of a mean and standard deviation. Yeah, I don't think I covered that part very well.
Yeah, and then in the KL divergence, you're forcing it to be a
Yeah.
mean standard deviation. Oh, I got you. Okay.
Yeah. So exactly. So the whole thing is like we're doing the KL divergence, I believe, between the standard normal, and the actual whatever distribution your model's outputting, right? So the KL divergence term is what enforces that we're learning a distribution, mean standard deviation, as opposed to just two random numbers. So yeah, that's kind of how it does the regularization. Yeah. Because, yeah, okay. In theory, yeah, because in theory, this KL divergence term, not in theory, it's not really making sure because again, like the whole reconstruction aspects is in the reconstruction loss. The KL divergence is actually making it harder for the model to learn. Not harder, but it's almost
Yeah.
like sabotaging the model, right? Because if you turn that beta term super high and like we just have standard normal distributions everywhere, well then we haven't learned anything because like everything has 0 and everything's 1, right? So the KL divergence is regularization in that it's making the model worse, technically, sort of, right? And imposing constraints on it in a way that makes it easier downstream to sample latent representations. Okay, that's it. Yeah, last question was on. All right. Cahoots were, I think, good. Just I gotta double check the answers. All right, this one didn't count for any scores. Sorry, Shoops.
Dang.
Sorry, Shoops. Maybe